So, what is the difference between a scalar and a vector? You do need to know what a scalar and a vector are in order to answer that question, don't you? Because if you don't know those, then you can't answer the question. Does anybody know what either of those words means? Go ahead.
Vector points in like the direction and tells you like I don't know. I don't know.
You got it without even realizing it, or without sounding super confident about it. A vector measures both size and direction. A scalar, oh, it's unfrozen, so you can't see this. Sorry, there you go. A scalar, please take your headphones off. You don't need them off on where you're doing this, unless you got a 4 out of 4 on this. Okay? Define a scalar. Well, it's not a vector. It's also a kind of measurement, but it's a measurement that only measures. Anybody? Anybody want to guess? Yeah. A couple examples of scalars. Let me give you a couple examples. Temperature. Speed. Mass. If you measure the temperature of something, you're just given a number, right? It could be positive 3 degrees Celsius or negative 3 degrees Celsius, but it's just a number. Speed, okay? How fast are you going? 50 miles an hour. Mass, how much mass does it have? It has 30 kilograms worth of mass, okay? Those are all scalars. Vectors have to include a direction. An example of a vector, the one we're going to get to know and love right now, is velocity. We've talked already about how velocity and speed are different, right? Velocity has positive and negative. Okay, you say, well, so does temperature. But velocity can also have, like, let's say I'm traveling 5 meters per second. I could travel positive or negative. I could also travel north or southwest, or, do you know what I'm saying? Like, you have got lots of different directions that it could be. We just haven't really entered that world until today, okay? Another one for vector is displacement. And continuing that list of things that we know and love, displacement, velocity, and what's that third one? Acceleration. I heard you say time. What is time? Is time a vector or a scalar? It's a scalar. Yep. For sure. Yep. Other things that measure both size and direction, another one that we're going to talk about a lot soon, next unit. We haven't really mentioned this word before, but force is also a vector. These are the ones that we're going to focus on right now. This is just another one that's coming to you soon. Okay, from a physics class near you. Okay. So that's the difference between a vector and a scalar. If you didn't know, you know now. Now you know it. Yay! What is the answer that is found when adding 2 or more vectors together called? So this is funny. So if we're going to draw a vector, because it has size and direction, when we draw a vector, we draw it like an arrow. I think somebody, Stella, did you say it was like an arrow? Or maybe you did. So you're going to draw that arrow because we're going to dissect our vector. So go ahead and draw your arrow, okay? There are 2 parts to an arrow. There's a head. That's where the pointy part is. And just like a coin, on the other side is the tail. So when we add vectors together, which we're going to do in just a minute, if we add vectors together, we might have one vector that goes like this, and then we're going to add another vector to it. When we add the vectors together, we add them head to tail. So you don't add them so that their points are pointing together. You add them so it's like you're going to follow a path. Okay, so I've got one vector that goes like this, and then maybe I've got another vector that goes like this. Okay, and so the path that I could take, I can either walk the blue path and then the green path to get from my start to my end, or I can add them together, and I can start here and I can end here. Okay, this red path is the same as the blue plus the green. Okay, and when I add the blue plus the green together, I get the red, and the red is what we call the resultant. The resultant vector. Okay, and we get that by adding vectors, and we do that by arranging head to tail. Indeed they are. Yes, we're going to get to know and love the Pythagorean theorem if we don't already. Okay, so the one that I just drew here is not a right triangle, which makes it a little bit less enjoyable, but we'll do that. We'll do things like this later once we know everything we need to know. Right now we're going to talk about the Pythagorean theorem because you know it. I know that you do because I know that you learn it in, I don't know when you first started learning it, maybe when you were pretty little, like in middle school or something like that. But if not, I'm hoping that at this point in your life, you have seen the Pythagorean theorem. What does the Pythagorean theorem state?
A squared plus B squared equals C squared.
Woo, she says that's right. Yeah, a squared plus b squared equals c squared. So everybody's got that memorized, right? You know that. You've been saying that to yourself for a long time. Like, I'm so cool, I can recite the Pythagorean theorem. Absolutely. Hopefully you've also proven it. It's super exciting. We need to know what these a, b's, and c's are. Is it just any random three parts? It's three parts of a what, first of all? Triangle, and it's even more specific triangle. It's a right triangle. So we're going to draw ourselves a right triangle. So I've got one side like this, and I've got one side like this, and I can add them together, and I can get my, what is this orange one called then? Yeah, in terms of the question 2. The resultant vector. Yep. It is the hypotenuse. Absolutely. And it is which of the letters, A, B, or C? It always has to be C, right? The hypotenuse is always C. It's always the longest one. The other two legs are put together at right angles, right? Does it matter which one's A and which one's B? It does not matter. A and B. We just know that these ones have to be the legs of the triangle. Okay. How are we doing so far? Sweet. All right. Next thing. Fill in the blanks with the correct choices. Before we do this, I want to know how many of you have seen sine, cosine, and tangent before. Sweet. That makes me so happy. Was that like slow to respond or like we've never seen it before? Awesome. You know why it makes me happy? Because it means that I get to teach it to you correctly. And I'm not saying that your math teachers don't. I'm just saying that a lot of times in my experience, students have come into me going like, I hate sine, cosine, and tangent, and they get really scared and really unhappy and they hate this. It's not that hard. And so I'll get you there, okay? So I don't want you to get upset because I'm going to teach it to you right now. Are you excited? It's going to be great. Here it comes. So if you've never seen this before, this is your opportunity right now to learn it, which means that I need your 100% focus right up here. If you have seen it before, pay attention too, because I might help fill in some holes, okay? So we'll answer this question a little bit, but here we go. We're going to learn some trigonometry right now. Woo! It's going to be good. So we're going to have right triangles. So you're going to draw yourself a right triangle with two legs that are very different sizes, please, and a hypotenuse. And I want you to mark the right angle of that triangle. Okay? I'm going to write down that these are what they call the trig functions. And again, if you've never seen this, it's totally fine because I'm going to help you out, okay? The trig functions are super helpful when you're dealing with right triangles if the Pythagorean theorem won't do enough for you. The Pythagorean theorem tells you everything about the sides, right? But it tells you nothing about the angles that aren't the 90-degree angle. The trig functions tell you what you need to know about the angles, okay? Now, I'm not going to get into the exactly why everything works, because I want to leave something for your math teachers to do, okay? But I'm going to tell you that the how to use it part, okay? So let me introduce you to a right triangle. You're like, I got this. I know this. I'm going to mark one of the angles that is not 90 with my favorite Greek letter for the day, theta. So if you look up here at my alphabet that's kind of falling down, so you got alpha, beta, gamma, delta, epsilon, blah, 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 blah. There's the one that looks like a circle with a line through it, okay? That letter, it's a Greek letter, so if you go to Greece and you look at the signs, like, McDonald's and whatever, they would all be written out using these letters, not the Roman letters that we're used to.
Oh, that's what those letters are?
That's what they are. Yeah, I know, right? It's cool, huh? So theta, welcome to theta. It's spelled in Roman letters. It's spelled Theta, theta, okay? And theta is a Greek letter that we use a lot for an angle. So it's kind of like how a lot of times if you're doing a problem and you don't know something, you just put an X, right? If there are 7 oranges and Larry takes 2 oranges, how many oranges are left? And you have to write that as an expression. You might, do like 7 and whatever. I can't remember what I said, but X is like your unknown. Theta is the unknown that we use for angles often. I don't know who picked it. I don't know why, but we just say, okay, it works. Now we're going to label other things on our triangle. So we picked a theta. The long side of our triangle is always the hypotenuse, because it's the long one, right? The other two, when you're doing the Pythagorean theorem, are just A and B, and it doesn't matter which one's which. But once we've picked a theta, now they do. There's one that's across, that you go across the triangle to get to. That one is called opposite. That one is called opposite. Okay? Because you have to go across the triangle to get to it. The one that makes up the other side of the angle theta, besides the hypotenuse, that one is called adjacent. Adjacent meaning next to. This side is called the adjacent side. And the really, really great part about trig functions is that my 3 trig functions that I'm going to tell you about in a minute relate theta with all 3 of these. And do you want to know the magic of this? If you can use these trig functions to figure out theta, and you know this thing and you know this thing, you all know what the triangle adds up to, right? The angles. It has to add up to 180, right? Every single time. So if I know this is 90, then I figure this one out, I can figure this one out with no problem. So this is like your key to understanding all triangles right here. Isn't that exciting? It's so fun. It's so cool. All right. So this is what I'm going to do. I'm going to pause that conversation because it's going to take more than 5 minutes to do that. And I want to make sure that I have fresh ears. So I'm going to give you a problem that doesn't require theta yet. Okay, so this is a separate problem I want to do first. And then we'll come back to this first thing in the morning tomorrow when I see you. Here's my situation that I want you to tell me about right now. Kermit the Frog walks 15 meters east, 10 meters west, and then 7 meters east. My question is, what is his displacement? When you're solving these problems, the very first thing before you write even down givens is to do what? It's silent up there. I didn't write it down. Picture. Let's draw a picture, shall we? Let's figure it out. Here we go. We're going to draw this picture. So he's going to go 15 meters east. So if I start him right here, we're going to go to the east. I'm just going to write that down as 15. How are we doing? So far, so good? That's the east. Yep. From there, he's going to go which direction now?
He's going to go west.
He's going to go west. So if this was 15 meters in the east direction, where is my next arrow going to go?
Back 10 meters.
Backwards, right? Students are always like, why does he do this? I don't know, because it's helpful for the problem, right? That's why, because it's an easy problem to do. So he's going to start there. I'm not going to draw it right on top because I'd get confused. Is he going to go all the way back to where he started?
Nope.
Not quite. Like maybe, I don't know, 2/3 of the way,
Yeah.
for example. Right, I know. All right, and then from there, I don't know why, although, you make fun of it, but I'm sure you do this. Like you walk somewhere and then you're like, oh crap, I forgot my digit. And then you walk back and forth. Does that ever happen to you? I'm sure it does. It happens to me all the time. Then he's going to go 7 meters east again. Here he goes 7 meters east. We're going to draw the resultant. The resultant is from the tail of the first to the head of the last. What was his displacement? Can you figure that out? Talk to your table mates. See if you can figure it out. I bet you can.
Minus 10.
Oh,
That's 5.
5 plus 7. That shows it to you, right?
So is it going to be more than 15?
No.
No. It's going to be something less than 15, right? So he walks 15, comes back 10. So how far is he from here now? 5 meters? And then he walks 7 more meters. So 5 plus 7 gives you?
12.
12.
Meters.
12 meters, but it's a vector, which means that I need both a magnitude and a direction.
Going east.
East. How are we doing? So far, so good? We're going to draw one more picture. Oops. You're like, where's the question? All right. All we're going to do is draw this picture. Beaker walks 4 meters north, 6 meters east, and then 12 meters south. Ooh, interesting. Let's do it. 4 meters north. It's important to think about the length of your arrows, right? So that it makes sense. So 4 meters, 6 meters is going to be a little longer to the east, and then 12 meters south. How are we doing?
Good.
Sweet. Can you draw your resultant? Tail of the first to the head of the last. Tail of the first to the head of the last. So tomorrow we'll solve this problem. I want you to know that there is some homework for tonight. I want you to solve question 1, and I want you to draw pictures for questions 2 and 3. You don't know how to solve questions 2 and 3 on page 89, but you know how to draw the pictures. So solve question 1, draw pictures for 2 and 3.
Are we going to split up the triangle? Yeah, we're going to split it up.
It's going to be great.